Hello students, today we are continuing the chapter wave in which we will study speed of traveling wave. Chapter wave and we are studying today speed of traveling wave. As we know that displacement y for an element, say consider here the element of string. So the displacement y for an element located at the position x along the x-axis is given by y function of position and the time equals to a sine kx minus omega t. Note that here we are considering that initial phase is 0 when the wave starts. So here we are considering that phi is equals to 0 initially. Let us mark this equation number 1. Now as per the given diagram, we are considering here that wave is propagating along the direction of x-axis, direction in x-axis, and we know that in this case element of the string at any position x moves up and down down up and down with respect to its position, and the wave travels toward right. For this you can see the figure given above. In this waveform, the displacement of the two different particles as shown with marking A with respect to each time instant when the wave is traveling. Say at the time t, the position of point A on the wave is A, and at the time after delta t, its position is at maximum displacement but has been shifted or has been displaced by a displacement delta x along the direction of the x. So in that case, we can say that the wave speed can be expressed as the ratio of delta x to delta t. Wave speed v can be given here. Wave speed v. The wave speed can be given here as the ratio of delta x to, where the delta x is the displacement of the point A shown in the figure along the wave propagation, and delta t is the time interval in which delta x displacement of the point A takes place. But remember one thing, the particles of the medium are not displaced along the x-axis direction. So as the wave moves towards right, Each point on the wave shows the phase of wave. On the other hand, points on the string points on the string do not retain their displacement. Now you can see the position of point A on the wave. Since at the time t the position of A on the waveform is same as after the time delta t. So it means that the argument given in the displacement equation, the kx minus omega t, must be constant to maintain the position A definite along the x-axis, or you can say to maintain the position A at the same displacement along the x-axis. So to retain the position of point A on the waveform, the argument kx minus omega t must be constant, since both x, the position, and the time t are variable. So to keep the argument kx minus omega t as a constant, we can say the differentiation of that argument with respect to time must be equal to 0, and from this we can get k multiply dx upon dt minus omega differentiation of time with respect to time equals to 0. Again, from this equation we can get k multiply velocity of the wave, that is dx upon dt minus omega equals to, finally we can write the velocity of the wave will be equals to k upon omega, where you know k is the number of waveform and omega is the angular frequency. Again, if the omega is expressed in terms of wavelength and the time period, then the same equation can be written as velocity of the wave equals to lambda upon t. That can again be written as the frequency of the waveform multiply its wavelength. Both are the equation number 2 we can consider here. The equation 2 is valid for all progressive waves. Also, we must have to remember that the linear mass density and elastic properties of a medium determine the velocity of wave propagation through a medium. That's all for today. We'll continue in the next one for this chapter.